All right, welcome back. Hope everybody enjoyed lunch. For our next speaker, we have another repeat Recon visitor, Natalie from Google Project Zero. How many years have you been coming here?
I don't even know anymore.
Yeah, that's amazing. I remember her doing Tamagotchi hacking presentations probably 6 to 8 years ago, and very glad to have her back to speak about some of the work she's been doing with messaging clients.
Great, thanks so much. So today I'm going to give a talk entitled Seeing Inside the Encrypted Envelope. I'm Natalie Silvanovitch, and I'm a security researcher on Google's Project Zero. Hey, sorry, is the mic working correctly here? Hello? Is that better? Awesome. So I'm Natalie Silvanovitch, and I'm a security researcher on Google Project Zero. And currently, I've taken up a bit of enthusiasm for instant messaging. I've been trying to find vulnerabilities in a number of messaging clients. And there's one problem that I found myself encountering over and over. And the question is, how do you test an encrypted messenger? If you think you have a bug and you want to send something inside the encryption to your target, how do you do that? And let's say you don't know how to find a bug and you want to see what that unencrypted protocol looks like. How do you do that? And I think this is important because these days, most remote attack surfaces accept. Okay. Hello? Yeah, so I don't know what this is going to sound like with two mics at once. I think I might just remove this guy and have him talking to the other one. Most remote attack surfaces these days accept encrypted input. I think the only one that doesn't really is SMS. I also feel that attack surfaces that process decrypted data are especially good because you know that a server won't have filtered the data or anything like that. So this is something that's useful to do, but unfortunately the encryption schemes are usually very complicated and often proprietary. So just to explain very clearly what my goal is, we have a user, and in an encrypted messenger or an encrypted protocol, you have a message, what the user typed, that is typically serialized, and then this gets encrypted, and that's another layer on the message. And then in a peer-to-peer network, it'll just go to another user and be decrypted. But sometimes it's more complicated. Sometimes you have your encrypted message, and then they add a server layer, and then this goes to a server that looks nothing like a server actually looks like these days. And this red layer will actually send a message to the server, and this is how they make messengers more compact. And then the network will put a different layer on your message, and that's how they communicate with the other client, and then that gets removed, and then you have your message. So what I really want to do is I want to see and change that. Because if you're an attacker, that's your vantage point. That's what you can see and change if you are attacking another user. And then sometimes I also want to see this. And this is not quite as good as being able to do it at the other end. But, if you're, say, almost have a bug and you're worried about whether the right thing is coming through to the other device, it can be useful for debugging. So why do I want to do this? Well, I've got all these logos that actually kind of all look sort of similar when you look at it. I'll see if I can remember what they all are. Signal, WhatsApp, Facebook Messenger, iMessage, Telegram, FaceTime, and then the last one is probably the only one that you don't know what it is. That's WebRTC, which is the component that enables video conferencing in browsers and a lot of other things. And these are all things that I've used these techniques to find bugs in, or at least look unsuccessfully for bugs in. So I want to share some of my techniques for that with you today. So when you're getting started with this sort of thing, what do you need to consider? Well, one big consideration is the platform. To start off, is it a mobile versus a desktop? Desktop environments tend to be a little bit easier because there's more you can do. And also, is it open versus closed source software? I'm going to focus on closed source software today because it's a more challenging problem. And another consideration is whether they're open versus proprietary protocols. Most of the time, they are proprietary protocols. Even if they say they follow a specification, they don't quite. But the more info you have, the easier this is. And then generally, there's kind of two types of messaging you have to worry about. What I call best effort, which is something like WhatsApp or Facebook Messenger or Signal, where you're sending a message, and if it takes 1 second for that message to arrive, which is a huge amount of time in computing, that's okay. Meanwhile, there are real-time protocols like FaceTime or calling in WhatsApp, and those need to be instantaneous or you get lag. Those ones are on milliseconds of time, and that means that whatever you do to send these packets has to be so much more efficient. So what are the strategies you can use? There's kind of three in general. One is to intercept over the network and decrypt and then send another thing if that's what you want to do. Another thing you can do is write a standalone client in software that sends the encrypted messages to the endpoint, or you can use an open source one if an open source one already exists. And finally, you can hook functions on the target. And I think this last one is the best one, and that's what I mostly use, and that's what I'll focus on today. So to start off, intercepting traffic. This is something that I've wasted a lot of time on. When I started looking at this stuff, this is what I thought would work, and honestly, my opinion now is it's never going to work. The problem here is that the documentation for a lot of these protocols, if it exists, lacks details. So even if you know the key, you're often not in a position to be able to decrypt a packet and know what every field means. And even if you did, where exactly are you getting this key from? Unless you know how to negotiate your own key, you're in trouble. One thing I have done, which I think is a very good way to get started, is sometimes you can remove the crypto libraries and then look at stuff over the network. So let's say you have a special libcrypto that if you encrypt it just mem copies, if you decrypt it mem copies, if you verify it always verifies. If you pull out your regular crypto libraries and then replace them with these, then if you sniff over the network, all your stuff is unencrypted. And that can be a really easy way to get started. And I actually did this with FaceTime. For a while, I was having trouble figuring out, had I actually identified the crypto function correctly? So I replaced them all with nothing, and then it still worked. So that made me think that there was nothing wrong with my understanding of the crypto that was making my client not work. What is problematic about that approach is it's not great if you're reporting bugs. Usually vendors don't like it when step one of your reporting process is pull out a library and replace it with a different library. Another option is to create a standalone client, create something that speaks FaceTime or WhatsApp or Facebook Messenger that you can use from the command line on your host. My opinion, if you get this working, it's the best and most stable solution. You have full control over it, and that's really good. But unfortunately, it has a heavy development cost. It means that you can't rely on anything in the code of the client. You have to understand how everything you send works so that you can reproduce it. What's nice about this is it's easy to redistribute. With hooking approaches, I have this problem where I'm reporting bugs with like 57 steps to reproduce because I have to tell the person how to hook their client because you can't redistribute someone else's binary. But it's easy if you write your own client. Although one thing I do think is a risk here is sometimes these clients can enable abuse. They can allow people to spam, they can allow people to use messengers on platforms they're not supposed to use them. So I think there is a risk if you write one and then you make it public that the vendor will start blocking it, not because they don't like people finding bugs, but because it enables other undesirable behavior. So another possibility is using existing clients. For a lot of the more popular messengers, there are third-party solutions. What I found, though, is most of these focused on functionality as opposed to coverage. When you're trying to find vulnerabilities, you kind of want to be able to do everything that the messenger can do. Meanwhile, if you're trying to write a client that will just, say, send a WhatsApp message from someone's command line, you're writing the minimum amount of code that will do that. So I looked at this a bit, and I found that most of at least the Facebook and WhatsApp client would do things like use web APIs to send messages when what I really wanted to do was to send the mobile protocol all the way to the other device. So I ended up not going in that direction, though one thing I did find useful was some of these clients had deserialization code, and I did occasionally, pull those out so that when I decrypted the message, I could run them on the command line and get a better feeling for what the contents of that message was. So here's an example where I actually did write a client. This was for WebRTC, which is open source software that you can use for video conferencing on browsers and some other clients as well, like Facebook Messenger. So having the code, I wrote a standalone client that could just call anything with WebRTC and send messages or fuzz messages. And with the code and with the WebRTC devs to help me, it took about a week to do. One thing I found very challenging was keeping it up to date. They would change the code, and the way I'd use the code didn't always mesh, and it wasn't like it was a supported client, so I'd have to fix it all the time. Although what was nice is this was one step away from writing a client that would send something on the command line and send it to itself so that you could do the whole path on your computer. And that enabled the ability to fuzz very quickly, which was very helpful. So hooking. Hooking is mostly what I use, and I feel it's the practical low-cost solution. At the very least, it's the best way to start if you want to see how buggy your software is. And then maybe if you find a lot of bugs, it is worth building a client. Like with writing a standalone client, it was a bit error-prone. Software updates are a challenge. Hooking a binary is really, really not supported, so it breaks all the time. But you can get good coverage using it. although as I complained, it's a challenge to distribute. It's a challenge to tell people how to reproduce bugs because you have to tell them what to do as opposed to just distributing the client you created. So there's kind of two different strategies here that are slightly different. One is you can use a debugger-like tool to hook at runtime, and another is that you can modify the binary. I feel modifying the binary is generally better for performance, like for sure, a lot better performance, and it also tends to be more stable, though runtime hooking is generally easier. So I'm going to give some examples of how I looked at different clients. I have an example of runtime hooking, which is iMessage, and then some of application modification. WhatsApp signaling are examples of Android applications where I was able to change the Java. And then WhatsApp calling is an example of an Android application where I had to change the native code. And then FaceTime is an example of just proprietary all the way down, and I had to start from scratch. So to start off with the iMessage example, Samuel Gross wrote this client for sending and intercepting iMessage. It works on a Mac, but you can use it to send whatever you want to a mobile device. Basically, he used Frida to hook incoming and outgoing messages. So Frida is really useful. It's one of my favorite tools these days. It's a Python-based real-time native function hooking framework. And it can also hook Android Java with limitations. I've found that the native function hooking is very stable and useful. The Java hasn't always worked as well, probably because I use a wide variety of Android devices. And the idea is that you can run this on any host, Android, iPhone, Mac, Linux, etc. And you just run a binary on the target, on your PC, on your Android phone, on your jailbroken iPhone, and then you can start hooking stuff via USB very easily. The actual hooking code is written in JavaScript, which is kind of interesting. One problem I've had with it is if you want to do something fairly simple with the hooking, it's easy. If, say, you want to do something complex in Objective-C on an iPhone, maybe not so much. So I ended up writing stuff with Frida that would run the simple hooking, and then I would have other binaries I would run later to actually do the processing. Because the problem with this JavaScript intermediary is it's kind of not quite real code. So here's the Frida code for intercepting iMessage. You can see you hook this dictionary function and then basically get the dictionary, and then there's another script which will send a message that just says replace me that you spawn before this one, and then it'll look for the message that has replace me in it, and then it will make the dictionary mutable, and then you can start changing keys of this dictionary, for example, the message key T. And that was sufficient. That was all that was needed to basically send any iMessage. So now I'll move on to the Android application example. I'll talk about Facebook Messenger and a bit about WhatsApp messaging too. I picked Facebook Messenger because it is the largest, most complicated messenger you will ever see by far. If you can do this, you can do any messaging client you will ever run into, I promise. So I'm going to go through about 10 strategies to figure out how messengers work. For most messengers, I think you probably need one of these, but for Facebook, I used about all 10. So the basic idea is I want to find where the message is encrypted and then insert some smally code, right after it's been serialized, but before it's been signed or encrypted. And then what I found was the easiest is I would set up a remote server with a little Python script. And whenever you hit a message, it would send the message to my server, which says, do you want to change this? Yes, no. And then I could change it. Then it would send it back. And then it would continue with the message. And I found that was just an easy interface for changing the message. So to start off, I decompiled the APK with APK tool and got the smally files out. But unfortunately, they're usually obfuscated. And also, Android applications have this tendency to just include tons and tons of code that no one ever uses. So here's an example of the sort of code you will get out from your typical Android application, which is unfortunately not that informative. So one thing I did right away was I looked for known libraries. Since Facebook Messenger says they use Signal Protocol, I looked for libsignal, and I looked for Java Crypto. And then I also later looked at some natives and log entries. So most EDE encrypted messengers include libsignal, but I find that most of them, other than actually Signal, don't end up using the full feature set and end up using, say, their own encryption functions. So usually what I'll start off with is just put your stub that sends your stuff to the server right where libsignal encrypts messages and see if that works. But this didn't work on most messengers. So then I moved to, this is my favorite cheap trick. I have a build of Android that has this send to the server stub in javax.crypto.mac. And you can limit this to only calling the stub when you're in the application sandbox. If you make it, access this file in the sandbox, and if you can access it, then send whatever you're macking to the server. You'll get tons and tons of stuff if you do this. Everything the application is doing a mac of, but sometimes this is enough to actually intercept your messages. Sometimes that is the only thing they're doing a mac of. And if that works, that saves a lot of time and it's super easy. I found about half of the messengers I looked at, this was sufficient just to hook this javax.crypto.mac. But what about the others? Well, if there's too much stuff going through that function, you can output the Java stack in the log. That's also not a very advanced strategy, but it often works. And then sometimes you'll find the right call stack that looks like it's encrypting. All of this, unfortunately, relies on the Java app actually using Java Crypto, which isn't a guarantee. Though usually even apps that implement their own crypto will still use the MAC signing from the Java platform. Once I was really desperate and output the stack every time system.arrayCopy was called. I did eventually find the encryption this way, but it was extremely time-consuming. You can also look for stuff in Smalley, but what I found difficult about this is there were 20 things called encrypt in, say, Facebook Messenger, and most of them didn't get called. So that's the problem when these applications include a lot of Java libraries. They'll all have stuff that's related to logging functionality or advertising functionality, and figuring out which one is the right one can be hard. This did work for WhatsApp, though. I just searched for obfuscated calls that took a byte array as an input and gave a byte array as an output. And there were only 3 or 4 of these in all of WhatsApp, so that was enough to figure out where encryption was taking place. And as I said, you can try this with Frida, but I haven't had much success with that working consistently. Another thing to look at is the natives, JNI. Because the Java native interface calls cannot be easily obfuscated. Usually they have descriptive names. So if they are named encrypt, they're probably good candidates for where encryption might happen. And one thing, if you try to do this, is you don't actually have to change the native at this point. If they're calling an encrypt native, you can just put a Java wrapper around it and then call that. And that's usually easier than trying to change the binary. Although this can still be problematic. Sometimes, you'll get file encryption instead of network encryption, and then all your files won't get encrypted properly. Then your application will never start again, and then you have to delete everything. I might have done this a few times. Also, I did make a script that would actually go through all the Smalley files and output a log entry every time there was a native call. Once again, this is maybe not the best strategy, but if you really got nothing to go on, sometimes that can help. So here's a question I had about JNI when I was looking at it. In a Java application, can native code ever be run without a JNI call? And the answer there is no, never. there will always be a JNI call every time you are calling native code in an Android Java application. And sure, they might start a process that does other stuff, but that's always going to be where you start. So that kind of narrowed down where you had to start looking at native code, because you always knew that it was going to start with that native call. And then another thing that can be helpful is log entries, and I find some apps are just full of these, and some of them are not so much. So this was kind of when I finally found some of the encryption in Facebook Messenger. It had this log entry, which meant that basically the code name for encrypted messages was salamander. And then that was something I could search for throughout the code, and it gave me the location of other encryption-related things. So yes, I found that after looking at this, signature verification failure is actually a pretty good place to start looking, just because it is on the wrong side, but if you can figure out where the signature fails, maybe you can then look for similar code where it gets signed, and then that's where you need to put your stuff in. And of course, in Java, it's very easy to add your own log entries. So when looking at this, I also discovered that apps usually have more than one location where they encrypt messages. They'll have the real message, and then they'll have where they encrypt the attachment. Sometimes they'll have a typing presence indicator that's either encrypted differently or not encrypted. Sometimes they'll send notification content differently. So for a lot of things, I would need different stubs in different locations if I wanted to capture everything that was going on. Or sometimes one was just enough if there was just one thing that I wanted to look at too. And the end result here was on Facebook, I ended up adding smally stubs in lots of different locations to capture everything, including wrapping some native encryption. And I was able to kind of get a fairly cohesive hook on it. Meanwhile, for WhatsApp, I ended up just adding this smally stub at the single location, which was the call that was obfuscated but had byte arrays in it. And that was enough to figure out it was encryption. But the other thing is I also altered serialized code at various locations to alter certain messages without understanding them. So to give an example of this, if I wanted to know if a file name could do directory traversal, sometimes it was easier just to figure out where they generated the file name for send and change it right there, as opposed to figuring out how to compose a packet that has that file name in it. So even though it's a good solution to do this where encryption happens, you can just do it wherever if there's something very specific that you're trying to test. And finally, I had messages. I was so excited when this worked. This is from Facebook Messenger. So an Android native example is WhatsApp calling. So WhatsApp allows video calling from mobile clients, which is kind of unfortunate. You can't do this on a desktop, so I had to do the hooking inside the mobile client. So I looked at the Android app, and unfortunately the native component didn't have any symbols. And unlike for something like Facebook, for this I did actually have to go into the native code, because it wasn't like they were calling this native every time they encrypted a packet. They were calling the native to start the sending, and then all the encryption happened in there. So this actually required there to be a native hook. So I found out, thankfully, that they used two open source libraries. libsrdp is purely open source. pjsip is proprietary, but they do give source dumps. And anyhow, I found the log entries, so I was able to find a memcopy where it would copy the packet to a buffer before encryption based on the logs. So to start off, I wrote a Frida script that would hook the memcopy, and it was cool. It took like 1 minute, and I was already hooking memcopy. But unfortunately, it was just way too slow. For video conferencing, it's like frames and frames, even a second, so it would lag so much it was unusable. But what was nice about this is I could debug binary changes with it. So as I was testing the changes I was making to the binary, I could hook them with Frida and kind of see, are my parameters correct, or that sort of thing. So I changed this specific memcopy to point to a function I wrote in ARM, And I put this where the GIF transcoder was, just because that's only used to send messages. And since I was just video conferencing, I knew I would never use this code. So yeah, I used this online ARM branch finder to figure out where to point it, and then pointed it to this function that opened called dlopen dlsim, and then jumped into a library that I compiled. So this didn't work right away. There were a few bugs in the code, but even after I fixed them, replaying the packets didn't work. And that's because of how the protocol that's typically used for video conferencing, RTP, works. It has all these fields, and the interesting one here is what's called the SSRC. So RTP can be used in stuff like browsers, and you can have like 5 Facebook calls open while you're streaming. And the reason that they don't collide is they use this thing called an SSRC, which is literally a randomly generated identifier that is different for every stream, and it's different every time you make a call. And my problem with this WhatsApp message was that my endpoint and my client was generating these random values, and they weren't updated in the stuff I was sending. So what was fortunate, though, is there's also a payload type that says, is this audio, is this video? And thankfully, each SSRC had a different payload type, so I was able just to correct them to the new one based on the incoming packets. So I fixed it, and sending the log packets worked, so that was great. Then I moved on to FaceTime. And FaceTime was interesting because it had very limited open source components. Luckily, it did run on a Mac, so that made it easier that I wasn't trying to hook stuff on an iPhone. But it was still time consuming, because I needed, in this case, to modify the binary once again to log the packets. So I started off by trying to figure out where it encrypted stuff. And thankfully, these symbols were very descriptive. So SRTP is the protocol they use to send video conferencing, and it's called SRTP encrypt data. So that's definitely where the encryption happens. And then it calls this system function, ccryptorupdate, that does encryption. And I used something called DYLD interpose, which is basically an environment variable on a Mac that can change what library is used for a specific function. But unfortunately, it requires setting an environment variable, which isn't possible for the video conferencing daemon. So instead, I used this project I found on GitHub that basically allows you just to add a dilib entry into a binary, so that then when this daemon started up, it would load my library, which would hook all the functions I needed. So here's just an example of one of my hooks. I'm hooking the ccryptorupdate and making it do other things. So I started off by hooking this to log stuff, and it needed some refinement right off the bat. One issue was everything gets encrypted, but I only wanted to care about RDP encryption, so I added something that checked what thread was calling it and made sure it was the right thread. Also, encryption is typically thread safe so long as you don't feed in the same buffer, but logging a packet is definitely not thread safe, so I had to add in a spin lock to make it so that you wouldn't be clobbering log entries with other log entries. Also, unfortunately, the way it was called in FaceTime, it didn't respect the return length. Because you're encrypting in place, you can just assume that the stuff you put in to get encrypted is the same length as the encrypted output. So I didn't have a way to change the length of a buffer that was encrypted, which would be necessary for some test cases. So I ended up having to patch the binary just a little bit so that it would respect this length and actually continue to process the binary of that length. So now I could alter my RTP in real time, and when I altered it, I could see on the FaceTime screen that everything was working correctly. But when I tried to do the same one again, like on WhatsApp, it didn't work. So here was kind of my mental model of how this worked right now. You have your audiovisual audiovisual content that's getting encrypted, sent over the internet, and then getting decrypted, and then I was just logging or replaying there. But like with WhatsApp, I had all these problems with RTP. And there was the SSRC and the payload, but then there were also these things called extensions. And extensions are supposed to be things that have nothing to do with what's in the audiovisual content. Things like screen orientation and whether you're muted and the quality. And wait a sec, don't these things like all depend on the content? So unfortunately, these extensions also had to be on the right packet. So I tried, logging these headers, and it didn't work. And then I realized that what ended up happening is that the header was actually not generated by the time it was encrypted. What would happen is the packet would be encrypted, and then it would be queued, and then the header would be generated, and then it would be sent using send message, which was actually quite problematic because there was an ordering problem. You would think that if you did encrypt, generate header, send message, and then another packet was generated, that it would happen in the same order, but that was not actually true. Like it would encrypt a packet, and then generate the header for the second packet first, and then send the packet that was before. So I basically needed to create some complicated logging that would detect what packet you had, and then wait for the header to be generated, and then log it, accepting that you might see 2 or 3 other headers before then, and you needed to log those and sort those out too. So this is my model now, and I was logging the encrypted content and logging the header of the full packet. And then when I was replaying, I was copying the payload from the log and then copying the header and fixing the SSRC. This didn't work. This is where I tried the network thing where I removed all the encryption just to make sure that I'd identified everything correctly, and with no encryption, this all worked. So then I realized there were a few more problems here. One was that each SSRC had a different crypto key, so I couldn't just use the encryption function when it was called. I had to extract the key. Also, I discovered that it was an XTS encryption mode with the sequence number of the packet as the counter. So then I had to log the sequence number and then make sure when I sent it a second time that it was in sync with the sequence number that was being used for encryption. So I wrote a way to basically calculate the correct sequence number, and then that basically worked. So then I had this basically set up, so you are creating your content, you're queuing your cryptor with your key, then I just crippled it so it wouldn't encrypt the packet at all, and then logged the entire packet. And then on the way, when you were replaying, once again, I'd log the crypto, or the cryptor, not do anything for encryption, wait until the header was generated, and then use that to calculate the correct header for this session, then put in the payload, then encrypt it, then send it off. And so this actually worked. We don't have Wi-Fi, so I'm not sure if this video is going to work, but I always joke about it. It is the worst demo video I've ever shown in my life. You make a FaceTime call, and it shows something on the screen, and then you make a FaceTime call again, and it shows exactly the same thing on the screen, if you can imagine that level of excitement. So my conclusions from this project. One thing I will say is if you're looking for amount of effort, I said the WebRTC was about a week for that specific project. And then for the Facebook Messenger, I think I worked about a month on that. Doing the WhatsApp calling was a couple of days to do the hooking, and then the FaceTime was about 2.5 months. So some of these were kind of shorter projects. Some of them were kind of larger, but that's kind of what your time scale is like. And I felt that after having done this, hooking was generally the best strategy when you take into account your time investment and your functionality. Standalone clients and network interceptions are also an option. I think I would do more standalone clients if I had more time to spend writing clients. Tools like Frida can make hooking easy in some circumstances. There's definitely a few situations where it made my life way, way easier. Otherwise, binary modification is usually necessary to do hooking. So I found a lot of bugs with these techniques, though they're not in this talk, but if you want to see all the bugs, you can run this query on the Project Zero bug tracker. And there's some that are still restricted, so keep watching. But it can give you an idea of what's possible with these techniques. And I'm going to end with you can do it. I won't lie. Many of these projects, when I started them, I did not think I would succeed, and they all worked out. So even though it can seem really daunting up front to start doing something like this, usually with enough time and effort, it is possible to make tools that can send messages in these contexts. So that's it. Thanks a lot. So questions, anyone? I guess not. Then thanks a lot.